So if we think about the time course of learning, we can identify three different phases of the learning process. Initially, when we're processing information, we're holding that information in working memory, and we might have some ability to retrieve that information after a short delay. We'll call that short-term memory. And as we'll see, neurobiologists believe that this is due to temporary increases in synaptic strengths among those neural circuits that are involved in processing the information. The next phase would be consolidation. That is taking this short-term storage of information and transferring it to a more long-term stable representation. And this is thought to require the hippocampal system. And of course then we have the long-term storage in the cortex itself. Now let's take a look at the work of Robert Bjork and others, and he has a lab that he calls the Learning and Forgetting Lab, which is kind of interesting to think about studying the process of forgetting. So what do people typically think is going on when we forget something? He argues that the sort of common wisdom is that learning is the storage of information, and forgetting is when that information decays. So the information itself is sort of disappearing from its storage site in the brain. Bjork argues that we should think of forgetting in a different way. Rather, there are two separate processes involved in this learning and process and memory process. He calls one of them storage strength, and this would refer to the strength and long-term storage of the information itself, and then retrieval strength, the ease with which you can access that information. And these are two separate independent processes, but they are related in interesting ways. So when we don't use information for a while, what we'll call disuse, it does not lead to a decay in the storage strength, Bjork argues. So it's not that the information is disappearing, really, from our long-term memory. That's not what forgetting is. Rather, he argues that disuse causes a decrease in retrieval strength, right? So the representation is there. The information is there in our brains, in the long-term storage systems. But the problem is that the retrieval systems have lost the ability to access that information. So forgetting is a loss of access. Now, to get a handle on these two concepts, storage strength and retrieval strength, let's take a look at some simple examples. So here we have a 2x2 box, storage strength, high-low, retrieval strength, high-low. So what would be something that has high storage strength and high retrieval strength? Well, take your address or your phone number, and especially if you've lived at the same place for a while, have the same phone number for a while. This is something that is well learned, and you can easily call it up from memory. Well, what would have high retrieval strength but low storage strength? Maybe this is a new phone number that you just learned, right? So it might be fresh in your mind, you've got access to it, so high retrieval strength, but you haven't learned it well. It is likely to be forgotten if you don't rehearse it, right? What about high storage strength and low retrieval strength? Well, this would be maybe your previous address. You knew it well, so Bjork argues that it has a high storage strength, but because of a long duration in which you didn't use that, you didn't access that information, you've lost retrieval strength. Now, how do we know it's still there, and the problem is retrieval strength versus a decay in storage strength? Bjork argues, well, if you just are reminded of the old address, you'll be able to very quickly reestablish high retrieval strength. In other words, it's as if the information didn't disappear, you had a problem accessing it, and when you are re-exposed to that information, that old address, you can relearn it very quickly. What about low storage strength, low retrieval strength? This would be, all the kinds of stuff that we learn in a typical day, but then forget. So here's his theory of disuse, the impact of time on the information that we've learned in the past. So here it is, storage strength then determines the rate of loss of retrieval strength. So if the information has a high storage strength, then retrieval strength will decay slowly, right? If it's well learned, you'll be able to hang on to it and have access to it for a while. The retrieval strength will decay slowly. If something has low storage strength, then the retrieval strength will decay rapidly. Now here's the counterintuitive relation that we'll explore. The higher the retrieval strength, Bjork argues, the smaller the gains in storage strength with additional practice. So he's saying that when information is highly accessible, like you have just been sort of rehearsing it, it is difficult, he argues, to increase storage strength. And that is counterintuitive, because we might think, well, if we rehearse something again and again and again, right, we should be increasing the storage strength of the information. We should be increasing the likelihood that we'll be able to store it in a long-term system. But Bjork argues it's not so simple. Okay, so this little graph here can capture sort of the basic relation. It's not intended to be an exact linear relationship like this, but it gets the idea across. When retrieval strength is high, right, the storage strength gain with additional practice is going to be low. When retrieval strength is low, Bjork argues, that's a situation where you can actually make greater gains in storage strength. Right, so this, he argues, suggests a rationale for spacing out your study sessions, and we'll see how that works in a moment. So let's go through these stages of the learning process. Working memory is thought to be a system of sort of loops of neural activity, and one very important region is called the dorsolateral prefrontal cortex. This area seems to be consistently activated whenever you have to sort of hold something in working memory, manipulate information. It can be a visual image, or it could be rehearsing a sentence or some numbers or whatever it is, or solving some mental math problem. Dorsolateral prefrontal cortex shows high activity. And in some of those experimental paradigms where they're recording from brain cells in this area, you'll find that high activity. You'll find nerve cells that show their highest activity during the delay phase of some of those working memory tasks. So the idea then is that when we are keeping something in mind, we are setting up these loops of neural activity, including dorsolateral prefrontal, hippocampus, whatever sensory cortex is involved in the information. If it's a visual image, then maybe visual cortex will be involved in this loop. If it's some kind of a thought or some auditory image, like our own voice saying something, then auditory cortex and other language areas might be involved in the loop. But that's the idea, that we have this ongoing loop of neural activity, and that's what maintains the information in this state in which we can access the information, manipulate the information, etc. Now, if we think about Bjork's terminology here, retrieval strength here, and let's say we're learning the Second Amendment, so we might read the Second Amendment a couple times, and after reading it, let's say we have to memorize it, we might read it a few times, and we might then be able to actually sort of repeat it. With repeated rehearsal, we'll be able to cite the Second Amendment. But over time, we're going to lose that, right? So that's this idea of decay, that our retrieval strength is going to decay. So after I stop sort of practicing the Second Amendment, and as the delay gets longer and longer, I'm going to lose the ability to retrieve that to some extent. And so that's indicated here by this fast decline in the retrieval strength. Now, from a biology point of view, how might we explain this? Well, the idea is, again, in the working memory system, we got the loops of neural activity. And when we are activating those neural loops, the idea is the synapses that are involved in that neural network here can show temporary increases in their effectiveness, in their strength. But it's only temporary, right? But that synaptic increase there would help explain why it is that you can retrieve the Second Amendment easily for some short duration of time after some rehearsal. But as time goes by, we lose that ability, and the idea would be those increases in synapse strength begin to decline again. So we get a decay or back to sort of the original synaptic strength. So this temporary change in synaptic strength here can help us understand why it is that information just rehearsed might be temporarily accessible, high retrieval strength, but over time, as those synaptic strengths decline, we're going to lose the ability to retrieve that information. Now, let's add our knowledge of the hippocampus to this story. So we know part of the working memory system will involve the hippocampal system, and you'll recall that study with that had Alan Alda in the study, and they were looking at people as they tried to learn the association between a face and a name, and they put them in the MRI scanner. And what they found is that during the training episode, right, when there was high hippocampal activity, that was correlated to later successful retrieval of the name-face pair. And interestingly, as the training continued, as a name and a face were repeated in the trials, hippocampal activity actually decreased with repeated trials. And the way Alan Alda suggested, it's as if the hippocampus sort of knew what it already knew, in a sense. There was there was high hippocampal activity for new name-face pairs, but as that name-face pair was repeatedly presented, hippocampal activity decreased. And here we have one possible mechanism for understanding Bjork's counterintuitive claim. That, remember, he was arguing that when retrieval strength is high, it's under those conditions that you're actually not making large gains in storage strength. So additional practice not very helpful to increase storage strength when the retrieval strength is high. And it may be that the hippocampus is sort of reaching a ceiling effect. It's maxing out. So additional practice is not going to help in increasing the long-term storage of that information. But this is just a suggestion from the research now. More work needs to be done in that area. But it's one possible way to understand Bjork's counterintuitive claim that high conditions of high retrieval strength, like when you are in the midst of rehearsing, we might think we're adding to our storage strength, but at a certain point we may not be making more gains in our storage strength. It could be that the hippocampal system is showing that relation. But here also it illustrates one of the misconceptions that learners sometimes have, and Bjork is very interested in uncovering these misconceptions. It may be that students believe, and we all might believe, that retrieval strength equals storage strength. So back when I'm rehearsing the Second Amendment, and it's, I got it down, I can say it again and again. If we then take that ease of access as an indication that I will remember it in the future after a long delay, we may be mistaken, right? So we can make the mistake that we think that because we have high retrieval strength, therefore we're going to have high storage strength. And that may not be the case.